Okay, we're going to prove a proposition on an alternate way of defining field generated by a set. So let's start with a set X, and I'm going to describe a subfield M, which is going to end up being the field generated by X. Well, what property should M satisfy? Well, first of all, it had better be that X is contained in M, right? Because if X is not contained in M, M has nothing to do with X, and we don't necessarily, I'll call this A. We're not going to get anything that's related to X. So X is contained in M, so M should have X within it if it's to be generated by it. And secondly, so this is sort of the very minimum, it has X. Secondly, if F is any other field such that X is contained in F, so if you have any other field that has X, well, M should be smaller than F. Then M is contained in F. So this is the smallest condition. I'm just going to write smallest. So if these two properties are satisfied, then M equals the field generated by X. Great. And conversely, such an M will always exist. M is the intersection of all fields containing X. It's the same thing, of course, as the definition from before. And this is an equivalent way of defining this guy. So M is always going to exist here. All right, proof. Well, let's let K be the intersection of all fields containing X. And by all fields, I mean all subfields of C that contain X. This is exactly this notation here. We show that F equals, that K equals M. So how do you show that two sets are equal? You need to show subset containment. Well, one of the subset containments is easy. It's this one. Let's start there. Since X is contained in M, M is one of these fields that K is the intersection of, right? It's all fields containing X. Hey, by part A, X is contained in M, so I have to intersect M here. And it's a standard set theoretic fact that when you take an intersection, every set in that intersection contains the intersection. So since X is contained in M, K is the sort of this big intersection of these F alphas. M is one of them, so that's certainly contained in M. For the reverse containment, we'll probably need to use part B. So what do we know? Well, we know that K is a field that contains X. Why do we know that? Well, K is the intersection of all fields containing X, so everything in the intersection has X in it. Therefore, the intersection has X in it. X is common to all of them. So we know K is a field that contains X. By part B, if we have any field that contains X, M is a subset of it. Okay. So we have, let's see, we have one of the containments here, and then the other containment here. All right, I think we have proved equality. And I actually, although the infinite intersection definition is fine, I actually like this definition, this what we proved here more. Let me end the proof. That's the end. M is K, because it tells us sort of how we might actually go at proving a description of a field generated by a set is correct. So let's see this in action. Let's prove, as an example, we're going to show that saying Q adjoin I equals P plus QI, P and Q, is true. Okay, we're going to show that that is correct. And when this shows up on exams or homework or whatever, One of the other ways we might say this is prove the set-theoretic description, or I might say describe the set Q adjoin I. One of those ways of prefacing this, they mean the same thing, namely theoretic. Namely, Q adjoin I is fine, like the smallest field containing X is fine, but if you're going to actually need to use the elements and you're going to want to make arguments with elements, you need to have an understanding of what the elements look like. Okay, so we need a second thing here. We need to not only have this idea of this field that can smallest field that contains Q and I, but we also need to be able to know without a doubt what the elements in that set look like. And those are related but different questions. Okay, so let's prove this. All right, so the right-hand side. Well, let's call the right-hand side something. Let's call this F. We know already that F is a field. Why do we know that? That was one of our videos in chapter 1, from chapter 1. So if you've forgotten how to do that, first try out the subfield test real quick. If you failed, go and rewatch the video. Okay, so F is a field from chapter 1, and so what we're trying to do is we're trying to establish equality of these fields. Great. Let me notice some things about F. We notice that Q and Q is a subset of F, right, where we have no imaginary part, and I is an element of F. So another way of saying this is that Q union the set containing I is a subset of F. Thus, by the proposition that we just proved, Q adjoin I is contained in F. Why? Well, Q adjoin I is the smallest field containing Q and I. F is a field containing Q and I. So Q adjoin I is a subset of F. That's this part B here, right? If F is any other field containing the generating set, then this guy is a subset of that. So that's one direction. We now need to do the other direction. And this will always be the easy direction. You just say, hey, I have a field. My generating set is a subset there. Therefore, it's the field generated by it is a subfield of that. Usually the harder direction is going to be the reverse direction. So let's take some P plus QI in F. Okay. Then P, Q, and I are all independently in Q adjoin I. Why? Well, P is a rational number, Q is a rational number, I is certainly in that field because it's generated by that. So what do we know? Well, Q times I is certainly going to be there because it's a field. We can multiply elements together. And we can add elements together because it's a field. So that combination is in Q adjoin I. Thus, F is a subset of Q adjoin I because every element of F is also there. So we conclude that our set-theoretic description is correct. Q adjoin I equals F, and F, of course, was P plus QI, P and Q and Q. I will ask you to prove something like this on an exam or on a homework. Oftentimes, we're not going to go in and prove it each time. We'll have a good enough understanding of numbers these are called algebraic numbers, the numbers we're adding in, so that we can just sort of make a guess and with almost 100% probability that guess is correct. But you do need to go through one of these proofs at least once, preferably on your own multiple times, just so you see how they go and the distinction between saying smallest fields containing a set and a specific set theoretic description of that, because they are different things.